right, everyone. Thank you for having me here today. As I said, Matthew Noyes is my name. I'm the software lead of the Hybrid Reality Lab at Johnson Space Center, and today I'll be talking to you about hybrid reality. So, a little bit of a summary to begin. NASA is currently on a mission to send humanity deeper into the solar system than ever before. And that includes the completion of programs like the Orion capsule, the Space Launch System, and considerable investment into the commercial spaceflight program. And in order to complete these programs, it's going to require the creation of new training and new procedures that our astronauts will have to learn. And we're looking at ways to decrease the cost while still maintaining the efficacy of traditional methods of doing astronaut training, engineering design, and so forth. Now, this is a picture of Neil Armstrong and Buzz Aldrin preparing using hardware mock-ups for their historic Apollo 11 moon landing, using the various EVA tools to grab rock samples. Now, this is a great way to learn how to execute procedures by using hardware mock-ups. But if you look around you, there's a very large number of distractions in the environment. They are surrounded by a large number of observers they can actually see. There's a lot of infrastructure in the building that they're able to see around them. It doesn't adequately capture what it's actually like to be on the moon. And what we want to do is see how can we use virtual reality technology to make the training experience feel a lot more realistic. In a situation like this where you're aware that you're being watched, you're going to get a stress response from that social anxiety. But that's completely different from what it's like to try to solve a problem in a life-threatening situation where there's nobody around to help you. That's what we're really trying to capture with hybrid reality. Now, you might ask, why do we want to go with that route if hardware mock-ups is able to solve the training conundrum very easily? Well, the answer is that Mars is a completely different beast from moon exploration. Instead of missions lasting days or weeks, we're talking about missions that are going to last months or years at a time. If a problem occurs, like with Apollo 13 with a tank explosion, we can't directly ask Mission Control for help in that situation. It may be 20 to 30 minutes before Mission Control even knows there's a problem, and another 20 to 30 minutes before our astronauts actually get a response. They are truly all alone up there. And that's what we're really trying to capture. So what exactly is hybrid reality? Well, virtual reality, as you know, the creation of virtual environments that you can interact with, has actually been used at NASA for about 20 years now. That includes programs like the X-38 spaceplane, training astronauts in certification procedures and how to use the jetpack in case their tether breaks, they can get back to the airlock, and so forth. But what virtual reality really lacks right now is the ability to have really convincing touch interaction. So there are technologies out there like gloves, which can give you a vibration if you touch an object. And there's currently technology being developed that's sort of like an exoskeleton that will pull on your fingers and give you the sensation that you're grabbing something. But it's still, at this point, nowhere near to what it's like to actually hold a real physical object inside your hands. So I like to look to science fiction as an inspiration for the next generation of touch interaction inside virtual reality. My favorite thing about Star Trek was a concept called the holodeck, a room that you could go into that was completely indistinguishable from reality, both in its visuals and how you actually touch things. Now, if you're a huge nerd like me, you spend your free time diving into the Star Trek technical manual. So let's look at a few quotes from that and see what inspiration we can take from the science fiction concept of a holodeck. One quote, "Matter conversion subsystem creates physical props using replicators. Replicated props are generally created when an object is likely to be touched by a participant." So the idea here is we're not relying upon some sort of sensory trickery to make you feel something. You're actually touching real-world objects. But we don't actually have replicators with today's technology. But we do have something similar. That is the 3D printer. 3D printers create objects using a concept called additive manufacturing, where you lay down layer by layer an object that you want to create using a single substrate, and over 24 to 36 hours, you'll end up with a completed object. That's compared to subtractive manufacturing, where you start with a block of material and you're milling away different things. Additive manufacturing is a pretty recent development in the hobbyist space, but it's proving to be a very versatile way of creating extremely low-cost mock-ups of tools. In this case, something called the pistol grip tool, which is basically like a space drill. Another quote, "Holodeck imagery subsystem creates three-dimensional images of simulated environments. Shaped force beams give physical substance to foreground objects, so they have the illusion of being solid." So what we're doing here is we're taking that physical matter that people are actually touching, and we're presenting an image of the object that convinces them that it's real. So here you can see on the left a 3D printed version of that drill, fully assembled, made of very low-cost plastic. Only cost maybe about $20 to actually make. Whereas on the right, we can see a virtual reality representation of that object that's painted over the top because we know where the object is located in 3D space using object tracking technology. And lastly, some props are animated under computer control by precision-guided tractor beams. So what does that mean? Well, in the case of a space drill, there are going to be parts that are actually moving, such as the end effector on the end, which you see spinning in virtual reality. But we're not actually going to be touching that portion of the object when it's spinning. So we can use traditional haptic feedback technology to vibrate the controller to make you actually feel like it's doing something, when in reality it isn't. That further drives down the cost even more. A similar related concept to this is 3D printing the outline of, say, a radar gun, and recreating the interface that you would actually interact with digitally inside the virtual environment. And we'll see an example of that later. So basically, what is hybrid reality? It's just combining together consumer virtual reality technology and tracked 3D objects together in one environment to create really good visuals and really good tactile feedback. It combines the best parts of the real and the virtual worlds into a much stronger and better sense of immersion. So in late 2015, we founded the NASA Hybrid Reality Lab. Our goal is to take concepts that were once only possible in science fiction and make them science fact. So let's look at some of the tools we're using to create our hybrid reality environment. The first of which is doing head and body tracking and giving visual feedback to a user. So the history of hybrid reality and virtual reality goes back to the early 1950s. But it was only around the late 1980s when the form factor that is associated with modern VR headsets was first utilized at Ames Research Center by Scott Fisher. Their goal was to create a space station maintenance procedure using wireframe models. And it's pretty stunning how designs created about 30 years ago are still pretty much in use today. This is an example of what NASA currently does for VR technology. We're using custom-designed headsets and custom VR rendering software to create training environments for our users. In fact, NASA sent up the very first instance of virtual reality in space by essentially taping a laptop to the astronaut's head. And then we have consumer virtual reality. We looked at a bunch of different headsets that are available. Here you can see the HTC Vive on astronaut Terry Virts. And basically, by looking at all the different features of current-day headsets, specifically the refresh rate, the latency, and most importantly, the room-scale virtual reality, where you can walk around in a small area and it tracks you one-to-one exactly as you're moving around in the real world, we found that Lighthouse is the most scalable solution for that at still very low cost. Using traditional motion capture technology like infrared cameras could cost anywhere from $50,000 to $250,000, whereas a solution like this only costs about $3,000 to $5,000, which not only means it's easy to deploy, it's also easy to send to other NASA centers and other NASA labs to grow the infrastructure that we can support with hybrid reality. Our next goal is to simulate reduced gravity and the sense of tactile feedback. Right now, a sister branch at the Johnson Space Center is working on the completion of the Active Response Gravity Offload System, or ARGOS. It's essentially a smart tether which attaches to your back, offloads your body weight, and accounts for your momentum in the vertical and horizontal directions to make you feel like you're in lunar gravity, Martian gravity, microgravity, or anywhere in between. Here we've actually combined virtual reality with the ARGOS system. The user is able to move around the 3D International Space Station environment by actually pulling himself through the 3D world. And the ISS is moving around him inside the virtual headset, which means there's no code that needs to be written to get this to work seamlessly. It just works. And lastly, we need to work on realistic graphics and sound, physics, and multiplayer capability. And that's where technology offered by the NVIDIA graphics chipmaker and the Unreal Engine 4 come into play. By offloading technology development for VR rendering solutions to a third party, this allows NASA to reorganize its resources to focus on content development that can actually be used by astronauts. It means we're able to leverage all the great work produced by senior developers at NVIDIA working on the GameWorks technology like Hairworks and the Flex SDK that improves the quality of graphics and fluids. And technology like VRWorks, including VR SLI and multi-ray shading, to make the world render much more seamlessly. And it allows us to tap into the open source community surrounding the Unreal Engine. We've created a series of applications that showcase some of the power of hybrid reality, the first of which is of the International Space Station. We've created a dynamic simulation of most of the interior modules frequented by American astronauts. Here you can see somebody exercising on the Colbert treadmill. That stands for the Combined Operational Load-Bearing External Resistance Treadmill, named after the comedian of the same name, as well as ARED, or the Advanced Resistive Exercise Device. Now, the physical interactions in our system was implemented using NVIDIA PhysX, which is used in many video games. And we've actually had real astronauts who've experienced the physics system for themselves, including the conservation of momentum and the dynamics of objects when they collide with each other. And they say that it actually feels like they're back in the space station. And that's exactly what we're going for, the sense that they're actually in the operational environment. Now, we currently have a very simple means to align the virtual world with the real world. It's good enough that your body's natural proprioception, the sense of where your limbs are in 3D space, can be used to grab objects inside the virtual environment. We're simply placing the controller on top of the real handrail, in this case, and the virtual representation is correlated with the virtual handrails. This allows us to make it very easy for astronauts to navigate around scaffolding in the real world. We can also track real-world objects. They can be weighted to weigh the same as what the real tool would weigh in the operational environment. What I mean by that is, say you're creating a mock-up of a 3D printed drill. That drill may weigh about 20 pounds on Earth. But if you're on, say, the moon, it's going to weigh 6 to 8 pounds. So if we make our plastic mock-up weigh 6 to 8 pounds, and the user is using it for 2 to 3 hours at a time, we can better capture how fatigue is going to affect their performance. And we can do that very easily by changing the amount of infill. That's the ratio between the amount of plastic and empty air inside of our 3D printed object. We can do hand tracking as well. This is the Manus VR glove. It's a very simple system that uses the HTC Vive controller to get the location of the hand and inertial measurement units to get hand rotation. And it represents the beginning of user interfaces that closely mimic reality inside the hybrid reality system. Now, in this case, I'm using the pistol grip tool to do a drilling procedure completely virtually, where I'm using a generic input controller to pass commands to the device in question. This in and of itself has a lot of useful applications in communicating how a tool actually works to other members of your design team and evaluating whether or not the tool is sized correctly to work in the operational environment. But still, nothing is going to beat the use of the 3D printed version of the drill when actually doing astronaut training that helps build muscle memory so they won't even have to look at the tool to do any operations. Now, the physics system, being so well regarded by astronauts, was so important that we decided not only to simulate rigid body physics, but also fluid physics as well. So we've integrated the NVIDIA Flex SDK for liquid simulation. Now, liquids in and of itself can be useful for simulating how a fluid experiment is going to be executed on the space station, or being able to stick your head inside of a rocket engine and watch the fuel flow occur in real time. But even more than that, we can also do fire and smoke simulation. So we could do a fire evacuation drill in ways that could never be done safely or cheaply with purely hardware mock-ups. In this example, a user is passing a stowage bag, which contains various supplies to me, over a networked distributed interface. Being able to train with other people inside virtual reality like this means that we could have people on completely opposite sides of the world that we could work together with. For example, Japanese astronauts at JAXA, European astronauts at ESA, and NASA astronauts at NASA could all work together in a single distributed International Space Station environment. It also opens the opportunities for doing more outreach activities, because people at home with their own consumer headset could log into a server and watch astronauts training in real time in a much more exciting way that can be achieved with regular NASA TV. Now, the cupola is one of the most interesting parts of this simulation. You're able to look out the window and look at the Earth below you. It's accurately modeled using photography of the Earth's surface. It's not a hand-painted facsimile. This was actually incorporated from Opaque Media Group, which is based right here in Australia, and originally created the model for Earthlight, which is a video game designed to make you feel what it's like to be a NASA astronaut. Working with groups like Opaque is very important because it allows us to improve the graphical fidelity of our simulators while allowing them to repurpose the same assets to generate profit for themselves, while also inspiring the next generation of engineers and scientists. And that sense of outreach is still an incredibly important part of NASA's mission that we're able to subsidize by the interactive entertainment industry. In this example, you can watch a virtual camera view of the space station where a robotic arm is reaching out to grab a vehicle and pull it in to mate with one of the space station hatches. This represents the situational awareness you would have if you were actually an astronaut. But we could also teleport you outside, and you'd be able to view everything that's happening in real time. This would be useful if you were running a training simulation. We don't want to have just the astronauts in the virtual world. We want everybody, whether it be the people running the simulation to the trainees themselves, to be able to operate inside this environment. Here we've 3D scanned the handheld laser tool, which is a radar gun that was actually used on board the space shuttle. We've recreated the digital interface and captured the sound effects from the real device, so it looks indistinguishable and behaves exactly the same as the real object, so they can learn how to use the tool inside virtual reality. And lastly, we wanted to capture eye adaptation. When you're orbiting the Earth at 17,000 miles per hour, you get a new sunrise and sunset every 42 minutes. But it takes your eyes about 30 minutes to fully adjust to the darkness, which means a significant portion of your time is going to be spent not being able to see properly. So we're capturing the ability for you to look up into the darkness and your eyes to adjust. We can do all of that in software, which means we can better capture the human error not just from a stress response, but also from a biological or physiological limitation. So just to quickly recap, we talked about object dynamics, 3D printed tools, 3D scan tools, microgravity fluid simulation, a really nice Earth model, and eye adaptation. All of these things together will allow us to make astronauts really feel like they're present in a simulation. The sad truth of human spaceflight is that the cost of failure is not just measured in dollars, it's measured in the loss of human life. And that is why we strive so much to make the system as realistic as possible. We've also done some work on planetary surface modeling. An example is the 20-foot habitat. It's a prototype habitat that astronauts would live in for months or years at a time. It's about 3 stories tall and has about a 20-foot diameter. It allows us to visualize the architectural arrangement of objects inside the virtual environment. A lot of the people who down-select different designs for habitats have no background in architecture. They may be management, or they may have a psychological background, or they may be student interns. So having them being able to walk around the environment, change the placement of objects in the environment, get a sense of how big the environment is, being able to do fit checks where we can tell if the environment is too small for them to maneuver around easily, All of that together can save a lot of time by doing it exclusively in software. And if we want to incorporate hybrid reality, it's as simple as incorporating foam core obstacles for them to interact with, which is not only much safer, but is also much cheaper because we don't have to invest in making it look realistic in the real world. We're working closely with MSI to define the specifications for their VR1 backpack. This is a gaming backpack that will be purchasable by regular gamers. But for us, it allows us to allow the user to carry the rendering software with them on their backs. This eliminates a lot of the issues you get with wire entanglement or issues with communicativity if using a wireless solution. So NASA is helping to drive the next generation of consumer products in the VR sphere. We're also working closely with a company called Fusion VR to help them with their Mars 2030 experience. This, again, is another video game, much like Opaque Multimedia's game, that allows you to experience what it's like to be a Mars astronaut. In this case, we're looking very closely at a model to do a visual inspection before operating it. And they've also done a lot of work to do rover simulation. And pretty soon you'll be able to play something like this yourself as well. Now, when collecting samples on the Martian surface, you would most likely use a tool like this to tell you what the mass ratio of the different elements inside that sample is. And using 3D scanning, we're able to make this model look extremely realistic. This is the real object, and this is the virtual object. And you can see that with a few minor differences, it's pretty much indistinguishable from the real object. Now, we covered a lot of topics today, and it's meant to be a very general overview of everything that we're working on. If there's anything that I want you to take away today from this talk, is that the reason why the NASA Hybrid Reality Lab is here today is all because of people like you. Because every time creative people raise the bar for artistic quality in virtual worlds, and every time technologists push the boundaries of human-computer interaction, and every time businesses disrupt new segments of the market that demand new forms of media and expression, you are all helping to pen the next chapter in the saga of human spaceflight. So thank you.